Steinhauer here, welcome back. We're going to start this video with a review of the last class. And this review question is, which of these stars is the hottest? The Sun, Betelgeuse, Deneb, Regulus, and Arcturus. And to give you a hint, I have given you the spectral classifications of each one of these stars. The Sun is a G2 star, Betelgeuse is an M2 star, Deneb is an A2 star, Regulus is B7, and Arcturus is K2. So quick, which one do you think is the hottest? Okay, remember, in order to do this, you have to know the spectral classification sequence. And for the normal stars, that goes O, B, A, F, G, K, M, where these are the hottest to the coolest. And I've done those with the opposite seeming colors, because remember, the hot stars appear blue and the cool stars will appear red. Which one of these is the hottest? It has to be Regulus, this B7 star. All the B stars are hotter than all the A stars, are hotter than all the G stars, hotter than all the K stars, and hotter than all of the M stars. A Betelgeuse is the coolest of all of these stars at the surface. By the way, I said surface, but I didn't really mention this in the last video. This is, of course, just the temperature at the surface. Why is it the temperature of the surface? That's the only temperature we can see directly, right? When we're looking at the sun, we're seeing the surface of the sun. We're seeing the photosphere of the sun. The temperature of the sun that we see is the temperature of the photosphere, and that is the temperature that we're talking about here, because that's really the only temperature that we can observe directly, the surface temperatures of all of these stars. Okay, great. So in this video, we're going to talk about, continue our discussion of how we determine parameters of stars. And at this point, our next parameter is measuring the masses of stars. We've already seen temperature, we've seen distance, we've seen luminosity. We've even kind of seen how we get radius, but we'll talk more about that later. Now I want to talk about mass. How do we determine the masses of stars? And the way we do that is by measuring the properties of stars that are in binary systems. So here's a picture of a binary star system. You've got two stars here, this one and this one, the two bright ones here. And if you were to play the sequence, you would see these two stars orbiting around one another, physically moving around one another. They are kind of like planets orbiting our own sun. They are in orbit around one another. They are gravitationally bound together. And the total mass of the system plays an important role in how fast these two objects will orbit around one another. And so we can use the observed properties of these stars, these binary star systems, to determine the actual masses of those stars based on the strength of the gravity between them. So there are several kinds of binary systems. Let's talk about them briefly. We've got these three kinds of systems that are determined basically by how we observe them. Visual binaries. In a visual binary, we actually see both stars orbit one another. Eclipsing binaries and spectroscopic binaries, we only see a single star, and that's almost every one of them. Visual binaries are rare, actually, in that they have to be fairly close to us, so that and far enough apart from each other that we can actually resolve both stars. Most binary systems are not that way. Most binary systems, when you look at it through a telescope or with your eyes, just looks like a single star. We infer that it's a binary system based on some other property of that object. So see only one star for both of these. For eclipsing binaries, we see one star pass in front of the other and see periodic dimming of the system. As one star passes in front of the other. And for a spectroscopic binary, we're looking at the spectral lines and noticing them shift back and forth. I'll say wobble of spectral lines. And we'll talk more about what that means in a minute. But this is important. About half of all stars in the galaxy are in binary systems or in some sort of multiple star system. And so the sun, I don't want to say it's unusual in not having another stellar companion, but it's certainly not unusual for stars to have a binary companion or some kind of multiple star system that it's involved with. And this is important because these are the stars that give us the information about stellar masses that we can use to make inferences about all the stars and find out how they work. Okay, so let's talk about these in turn: visual binaries, eclipsing binaries, spectroscopic binaries. Here is an example of a visual binary. Visual binaries are pretty simple. We can see both stars, in this case, star A and star B, and we can, over the course of weeks or months or years or centuries, watch those two stars orbit around one another. So you'll notice in this particular example, star A is the brighter one, and you'll notice from 1900 to 1970, we're talking about 70 years of observations, this system goes through about a full orbital period, right? So let's watch the bright star moving to the right, moving to the right, moving down, and then from 1940 to 50, circled all the way back around and was pretty much back where it started in 1900, and then the entire pattern repeats itself again. The orbital period of this system is about 50 years, because it takes about 50 years for the system to get back where it was when it started. And so we can observe directly both of the stars and watch them orbit one another. That's a visual binary. But these are unusual. They have to be fairly far apart and have to be very close to us in the galaxy for us to be able to physically resolve those stars. Most stars, we don't get that information from. How do we know they're binaries then? Well, again, they appear as a single star, but sometimes you have a single star that undergoes eclipses. So here's an example of an eclipsing binary star. It might be that you've got two stars here, one smaller, one bigger, and it might be that at certain times you're seeing the full light of both stars, but sometimes one star might pass in front of the other, and then at other times the other star might pass in front of the first. And during those times, the total light that you're getting from this star changes because you're not getting the full light from both stars during those eclipses. So this is something called a light curve. A light curve is simply how bright something appears as a function of time. So again, most stars are perfectly flat, right? They don't change in brightness, at least on the order of days or hours or weeks, right? That's just a flat line. But if you've got an eclipsing binary, some interesting things happen, right? During the times of the eclipse, the entire system will get a little bit fainter as the light from one of them is blocked by the other star. And so, and in fact, in eclipsing binaries, it's almost always the case that you get two of these eclipses per orbit. Once when the first star passes in front of the second, and the other when the second star passes in front of the first. And so the entire period of this one is the time that it takes to go through both of these and then back again. And so you see these periodic eclipses, and this is an eclipsing binary. A spectroscopic binary is similar, except we don't necessarily see the eclipses. We're using the Doppler effect to give us information about this particular binary system. So for instance, let's say the Earth is over here somewhere. Let's draw it in as some sort of blue dot, except obviously it's going to be way further away than that, based on the size of and the scale of this, but you get the idea anyway. And so let's say we've got star A and star B, and they're going around each other. Now, in this diagram, to make it a little simpler, I've kept A at the center and star B is moving around it. That would happen if star A were much, much more massive than B, which is kind of how the planets work. But if star A and B have similar masses, they're actually both orbiting a common center of mass. But let's take that out of the situation for a minute and just look at the spectrum of star B, right? At this point in the orbit, at the top, star B is moving in this direction, and that star is going to be moving towards us, and so its spectral lines are going to be blue shifted or shifted to the left on this diagram, right? And then half a period later, star B is on the bottom, and it's going to be moving away from us, and its spectral lines will be red shifted or shifted to the longer wavelengths at that point. And so if you watch the spectrum of star B by itself, you'll see its spectral lines wobble back and forth. Blue shifted when it's moving towards us, red shifted when it's moving away from us, and constantly moving back and forth as this object orbits the other one. Now, in practice, we'll see the spectral lines of star A and star B. So but when star B is moving towards us, star A is moving away from us. And when star B is moving away from us, star B is moving towards, or star B is moving away from us, star A is moving towards us. So it's the opposite. So when we see star A red shifted, we'll see star B blue shifted. And so you'll sometimes see both of these sets of lines, and they'll be wobbling in opposite directions as the stars orbit one another. And so that's a spectroscopic binary. A spectroscopic binary, because we know it's a binary by watching its spectral lines and observing them shift in radial velocity back and forth over time. Okay, now how does this give us mass? I said that this was going to give us mass. You might remember Kepler's third law of planetary motion, p squared equals a cubed. Well, Isaac Newton figured out why that works and extended it to objects that are other than orbiting the sun. Because p squared equals a cubed only works for objects orbiting the sun. But Newton realized that there was a more general law under there that all objects that are orbiting other objects obey a p squared equals a cubed law, but it's not, he figured out what the proportionality constant was. And this is the full equation. P squared, the orbital period squared, is proportional to a cubed, with the proportionality constant being 4 pi squared divided by, this is capital G again, our universal gravitational constant, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, times the sum of the masses on the bottom. And that's the sum of the masses of the two objects that are orbiting one another. So how does this work? If you can measure the orbital period of the binary system, and that's easy, no matter what kind of binary system you have, right? If you can figure out how long it takes to go around, either by measuring the timing of the eclipses or measuring the timing of the wobble of the spectral lines, or by actually physically watching them do it, you can measure P. Measuring A is harder, especially if you've only got an eclipsing binary or spectroscopic binary. But if you've got a visual binary and you know how far away it is, then you can actually measure A as well. And if you know what P and A are, then you can measure the sum, and then you can solve for the sum of the masses themselves. And you can use other facts like the ratio of the masses, the ratio of the radial velocities, and things like that to solve for the individual masses themselves. And so we can use the fact that the more massive the stars are, the faster they'll be going around each other to actually determine what the masses of these the stars actually are. And when we do that, we find that the most massive stars in the galaxy are about 100 solar masses, and we find that the least massive stars are about 0.08 solar masses. And this is, we see objects that are lower mass than this, but they aren't stars anymore. And we'll talk about why that is and what we call those objects in a future video. Okay, that's the masses of stars. We'll come back next time and talk about the Hertzsprung-Russell diagram. Thanks for watching.